Alright, so today I'm going to be running through this internal flow problem here. It's going to deal with Bernoulli's equation for pipe flow. As you can see, we have this setup right here and a bunch of givens, and let's get started. So if we look at what we're given right away, we have the volume flow rate, which is going to be helpful. However, notice that it is given to us in gallons per minute, so we're definitely going to want to address that because that's not a unit that we really tend to work with. And then from there, we have the density of the fluid, the viscosity of the fluid, the diameter of the majority of the pipe is given to us right here as being 0.75 inches. And then the second diameter is 1/2 inch, and if you'll notice, according to the diagram, that is only occurring right here at the very end of our pipe, and the rest of it is this 0.75 inches is going to be the diameter of basically the entire rest of the pipe. So that's going to be the diameter we're generally going to be concerned with. And then we're also given the roughness height, which will be helpful a little bit later on. And so from there we have this conversion, which we'll use pretty soon here, and then these minor loss coefficients. So this is going to have to do with our head loss, which we will get into pretty soon. But these coefficients are sometimes given to you in a table format, so you need to kind of know what to look for. But this is pretty simply laid out for us, where we just have the coefficients for 90-degree elbows, which are these elbows that you see here, these kind of just bends in the pipe. And then for the fully open globe valve, that's what you see right here. And then finally for the fully open faucet, which is what we have right at the end here. And you'll notice that it's giving us the coefficient and it's noting that it applies at the entrance of the pipe, which we'll explain later, but that is going to let us know that we want to use the velocity and the diameter of the pipe at this end, where the diameter is still 0.75 inches, and not at this end where the diameter is smaller, because it says we're concerned with the diameter at the entrance of the pipe, which is when it's still large. And then finally, it's asking us to find the initial pressure of the system, and by initial, I guess what I mostly mean is the pressure at point 1, which if we want to name our points now, we'll call that point 1 and this over here point 2. And we're being pretty intentional with where we put our points. I think it's kind of obvious given just kind of the setup of everything, but we definitely want point 2 to be right at the outside of this final point, because that makes our life a lot easier, because the pressure here is going to be 0, the gauge pressure, because we're open to the air, so it's just atmospheric pressure there. Alright, so now that we have that kind of explained for us, let's get started. So first thing that we want to do is get our units in order. So you'll notice that the diameters that we were given are in inches, and we definitely would prefer that those be in feet, just given the fact that all of our other information is in feet. So let's start there, because that's a pretty easy place to start. So first we want to switch the first diameter into feet, and we can do that by just dividing it by 12, and that will give you 0.0625 feet. And then we'll do the same for the other diameter, just divide that by 12, and that will give you 0.04167 feet. Okay, so that's great. And as you start to do more and more of these problems, you'll notice that you're dealing not just diameters, but also a lot of area calculations. So why don't we just go ahead and find the areas for each of these kind of pipe sections as well while we're at it. So the area is going to be pi over 4 times the diameter squared, which in this case is going to give us, for diameter 1, 0.003068 feet squared. And then for the second diameter, pi over 4 d2 squared, this is giving us the cross-sectional area of the little nozzle here. This is going to be 0.001364 feet squared. Alright, so now that we have those, like I mentioned earlier, that volume flow rate being in gallons per minute, we don't want to deal with that. So let's address that now. So we have 12 gallons per minute, and you'll see up here that we are given this conversion that 1 gallon per minute is this number of feet cubed per second. So using that conversion, we can go ahead and convert this into feet cubed per second, which is a much more friendly unit for this problem. So all we have to do there is multiply the volume flow rate that we were given by that conversion factor. And now our new Q is going to be 0.026736 feet cubed per second. And that is well and good, but in these types of problems, what we're primarily concerned with is velocities. So we're going to use this new volume flow rate to give us the velocities that we care about. So in order to get the velocity of the 0.75 inch diameter section of pipe, or basically almost all of the pipe that we're concerned with, we'll go ahead and take our Q and divide it by the cross-sectional area of that section of pipe. So that is our Q value that we just found divided by the area of 1, which is this value that we found just a moment ago, and that will give us the volume throughout the pipe in the 0.75 inch diameter section as being 8.715 feet per second. Alright, and then we're just going to go ahead and do that again so that we can find out what the velocity of the fluid is as it exits the nozzle. And we take our same Q because the volume flow rate is conserved throughout the pipe. The flow is steady. And we go ahead and divide that by, oh, made a little mistake here. We want this to be area 2. Alright, so now we can go ahead and divide that by 0.001364. And that tells us that the velocity coming out of the nozzle is going to be around 19.61 feet per second. And this is a good time to kind of stop and ask yourself, okay, does this make sense? Yes, it does, because the area gets smaller at the nozzle, so the velocity of the fluid increases. Just kind of that conservation of mass stuff that keeps coming back. Alright, so once we've done that, a very common theme you'll notice for these types of problems is that we care a lot about the Reynolds number. So why don't we go ahead and calculate that next. Okay, so for this part, pretty familiar equation by now, I'm sure. So the Reynolds number equation is going to be right here. And you might be wondering, okay, well, we have 2 velocities that we just calculated and 2 different diameters. Which do we care about? Well, judging by just the way the problem is set up and, yeah, just the majority of the pipe being dealing with the 0.75 inch diameter and the first velocity, we're going to go ahead and say that we care about V1 squared and D1 over the viscosity. Alright, so using some of our givens here, we had 1.94. Velocity 1 we just calculated. Square that. The diameter 1, what was that? That would be in feet, 0.625. All of that over the viscosity, which was given to us as being 2.34 times 10 to the -5th. Alright, so once you punch that into your calculator, you end up finding a Reynolds number of 45,160. And now you stop and ask yourself, okay, so does this mean that I have turbulent flow or laminar flow? Well, the kind of threshold number is 2300, and this number is definitely greater than 2300. So we have turbulent flow here. Alright, so now that that is out of the way, let's get into our pipe flow / energy equation. So the general form of the equation, I'm going to write it out here, just a few different terms. Alright, so now let's talk about what each of these terms are. So first we have the velocity term, and then this alpha here, which is determined by our Reynolds number and our type of flow. So for turbulent flow, our alpha is going to equal 1. So for now, we can basically just disregard that. And then we'll have our energy due to our height difference, or our z terms, our pressure terms, and then we have this term here, this Hn. However you might want to kind of denote what that term is, it's essentially just the kind of energy being added into the system from something like a pump or a blower. And if you noticed in our system here, there really isn't anything that is contributing energy in that way. So we can just go ahead and say, okay, none of that going on here. And then another thing that we mentioned right at the beginning is that we can take the pressure at point 2 to be 0. So that term goes away as well. Alright, so that is good. Now we can also note that I've written here that rho is the same on both sides. That's true because we're not assuming that the density of the fluid is going to change at all throughout this system. So if for whatever reason the problem was a little more complex, you could go ahead and put the different values of rho in there. Okay, so now since we were asked to solve for pressure, we're going to just go ahead and rearrange this equation, and just kind of doing some algebra, moving the terms around, solving it in terms of everything else, solving for P1. So just going to go ahead and write it out like that. And I'm going to be a little bit intentional about the way that I group my my z terms here, just to make it a little more intuitive for us. Alright, so that kind of change in elevation term for our z's, if we just kind of take a look at our system here, if this is point 1, we can just call this down here to be z equals 0, and our z direction is going up. So our z2 then is going to be this 10 feet that we go up plus this 10 feet that we go up. So our final z is going to just be 20 feet, meaning that our z2 minus z1, or our delta z, is going to be 20 feet. So that's an easy one that we'll be able to plug in right there. Alright, so now let's start talking about head loss. Head loss is made up of two main components. So we're going to be dealing with our major and our minor head losses. And I think that these are also things that can be denoted in a few different ways, but I'll just try to keep explaining as I go so that there's never any confusion. I know that major head loss is sometimes described as friction head loss. So whatever way you may have heard it, we'll calculate them and it'll be pretty clear, what each term is coming from. Okay, so let's start with our major head loss. So the equation for that is going to be this friction factor, delta x over the diameter times the velocity squared over 2g. And this delta x is just going to be the length of our pipe. So we can go ahead and calculate that really quickly. That's a pretty easy one. If we just say Okay, so we have 15 plus 5 plus 10 plus 10. Alright, so that is 15 and 5, 20 plus 10 is 40, and then we also do want to consider these elevation changes too, because the fluid is flowing through the whole length of the pipe, so that turns out to be a length of 60 feet. Alright, so now all of these things are known except F. So what do we do about F? This is the time when we use our Moody chart, since our flow is turbulent and that's the only way to determine what our F value is. So the information that we need to use our Moody chart are the Reynolds number, which we found to be 45,160, and then the ratio of our roughness height to our diameter. And the roughness height we were given as being 5 times 10 to the negative 6 feet, and our diameter in feet is 0.0625, so this ratio comes out to about 8 times 10 to the negative 5. Alright, so with these two pieces of information, this is when we can move over to our Moody chart, which I just have up here waiting for us. Alright, so first things first, let's start with our Reynolds number. So this is using a log scale. 45,000 is going to be coming after 10 to the 4th. So this is 10,000 right here. So then this number is 20,000, 30,000, 40,000. And so 45,000 will be somewhere right in here. So we're just going to go ahead and draw this line all the way up as straight as we can, right around our Reynolds number point, which is about 45,000-ish. Alright, so now that we have that, we can go over here and look at our relative pipe roughness. So our value was 8 times 10 to the negative 5th, which is going to bring us somewhere in between these 2 points. But you'll notice that as we get kind of further along in the graph, these two lines, this one and this one, kind of come together. So we'll just kind of shoot for somewhere in between them and stay on trend with the other lines, and you'll see most of them really do come together right around here. So we're just kind of trying to keep them parallel with those lines all the way through. And then we stop when we hit this point right here where our two lines meet. And this is going to give us, if we just go ahead and trace this over to this axis over here, that is going to be our friction factor. So again, you kind of have to eyeball it. I would say this is roughly 0.022 maybe. So we're going to go ahead and use that value for our F. Alright, so now let's go ahead and plug things in. So HF. Our friction head loss is going to be 0.022 times, the length was 60 feet, the diameter of this region of the pipe, and then multiply that by the velocity squared over 2g. Remember, we're in SI units, so none of that 9.81 for gravity. We're only using 32.2 on this problem. That is definitely an easy way to get tripped up, so be careful with that. Alright, so this turns out to be 24.91. Okay, great. So we have a part of our head loss, but not all of it. We now need to worry about our minor losses. Alright, so for our minor losses, we also have an equation for that. So our minor losses are going to be the summation of all of our coefficients times the velocity squared over 2g. Okay, so the summation term is important here because depending on the number of kind of changes in geometry or things like that, you're going to need to continue to add that number of terms. So in our case, we can just go ahead and bring the velocity squared over 2g out to the outside. So we have 8.715 squared over 2 times 32.2. We're going to bring that to the outside, and then if we take a look back here at our diagram. Alright, so what do we have? We have, let's count our 90-degree elbows. We have 1, 2, 3, 4 of those, 4 90-degree elbows. We have 1 glow valve, and we have 1 faucet. Okay, so take note of kind of the K values here, and then we're going to go ahead and plug that information in. So we have 4 times the elbows, and the K value for that was 1.5. We had 1 fully open valve and 1 fully open faucet. Alright, so that's kind of how we set that up. And this will give us a value of 21.23. Okay, so now we have all of our head loss accounted for. We have our delta Z, we have velocity is known, G is known, rho is known. We have everything that we need to solve for the pressure at point 1. So let's just go ahead and plug in. We have our rho, we have G, we have V2 squared over 2G. Remember that alpha value went away. It is technically here, but just a coefficient of 1, minus our V2 squared over 2G and an alpha of 1, plus our delta Z, 20, plus our major head loss, 24.91, plus our minor head loss, 21.23. Alright, plug that into a calculator, and you find that the pressure at 1 at the entrance of our system is going to be 4,431 psf, or if you divide that by 144, because that's pounds per square feet, or pounds per square foot, divide that by 144 to get that number in pounds per square inch. Alright, so that is a pressure measurement. Okay, so not too bad, definitely pretty time consuming, but conceptually I think as long as you know the process, know the equation, definitely doable. But now something that I kind of want to think about is if that, let's pretend that our Q is a lot lower. Let's pretend that our Q is now going to be, let's say, 0.482 gallons per minute. So if we slow things down a whole lot, how is that going to affect not just the pressure that we were trying to find, but also the head loss throughout the whole system? So if we go ahead and change that Q value, that doesn't change everything. We don't have to do everything all over again, but there are a few things that we definitely want to take a look at again. So now that our Q is 0.482 gallons per minute, once again, we don't like gallons per minute. We want feet cubed per second. So let's do our same conversion that we did earlier. Multiply that by our conversion factor that we were given. And that will give us our volume flow rate in feet cubed per second. Alright, and now we want to know the velocity because that's the number that we tend to deal with. So the velocity here is going to be that Q that we just calculated over the area, which we wrote down earlier, if you will recall, was this value. So our velocity is now 0.35 feet per second, so significantly slower than earlier. And our V2, which is the velocity as the fluid exits the pipe through the faucet, is going to be 0.7 0.874 feet per second. Alright, so a little bit faster than the velocity of the fluid throughout the majority of the pipe, but still pretty slow compared to what we were dealing with earlier. And then probably the most important thing that I want you to pay attention to as I go through this part of the example is our new Reynolds number and what we do with this information. So if we do the same calculation, but now with our new V1 value, divided by our viscosity, that number is going to come out to be 1,814. And if you remember, our threshold is 2,300, and this number is less than 2,300, meaning that our flow is laminar. Alright, so this changes a few things. Our general calculations are pretty similar, but it's always good to practice both types of flow because you want to remember the differences between them and kind of how you approach it. So first of all, our alpha is now going to be equal to 2. We don't have to deal with that quite yet, but just always good to make a note so that you don't forget, because I think it's one of the easiest things to forget. Alright, so then, now that we have that, let's consider our head loss. So for our major head loss, we still have the same equation, but the way that we find our friction factor is going to be a little bit different, or really a lot different, and arguably quite a bit easier for laminar flow. So F for laminar flow is just going to be 64 divided by our Reynolds number. So none of that Moody chart stuff. We just go ahead and divide 64 divided by 1,814, and that gives us a friction factor of 0.0353. Awesome. Okay. So now with that, we can go ahead and plug in, find our major losses. Delta X is still 60, diameter is the same. Velocity we found earlier to be 0.35. And this comes out to be just 0.06446. So right away, you'll notice that our major losses are very small compared to what they were earlier, like way smaller. And we didn't decrease our velocity by that much. So it's a very, very strong effect that this has on our friction losses as things begin to move slower. Alright, so now let's do our minor losses. So, same equation as before, nothing changes here, except that now we obviously are working with a different velocity. So we have our velocity of 0.35 squared over 2g, and this is the same as it was because our configuration hasn't changed at all. And that comes out to be 0.0342. Alright, so again, pretty small number. And then, if you remember our equation, P1 equals rho g times V2 squared over 2g times alpha minus V1 squared over 2g times alpha plus our delta z term, which was z2 minus z1, plus our losses. Alright, so we have everything we need. We can go ahead and plug in. You know the drill at this point. Plug in all of our knowns. V2 was 0.7874 squared over 2g. Now we have this alpha of 2. Plug in this term. With its alpha, also 2. Delta z is still 20, plus our losses that we just calculated. Quite a long expression there. Alright. And once you plug all that into your calculator, you'll find that the pressure at our inlet is going to be 1,275 psf, or about 8.859 psi. Alright, so you'll notice that is a decrease in pressure of about 3,156 psf. So that is a pretty significant decrease if you remember our value earlier and our value now. And so much of that has to do with just how much less friction there is in laminar flow compared to turbulent flow. Our losses were way smaller for our laminar flow. So yeah, it's just important to kind of think about why things are happening the way that they're happening, kind of double check your logic, make sure everything is making sense to you, making sense logically. I really hope that this video was helpful. Have a great rest of your day.